Let's continue with the talk of the Rishabh, who is PhD student at a supervisor, and we continue talking.
Okay, so yeah, thank you so much everyone for having me, and thank you so much Professor Khan for inviting us here. So when we say that this discussions on graph monoids and graph algebras, it's quite an ambiguous term. It's like a discussion. Is there? So what do you discuss? It's a lot of things that needs to be worked out. So before we get into why we should do this, the thing is that if you ever want to study graph monoids, why would you go through all the trouble? Why would you learn something which is new unless and until you want to solve something? So let me get into this, that why was I interested in this, but it came from a lot of twists and turns that I came into this graph monoids precisely. And I must say that initially I did not appreciate it, that how nifty this trick is. I came to this idea of graph monoids from something which is, and I think by now we can use this acronym of LPAs, calling it Leavitt instead of using Leavitt path algebras. I came to this idea from the construct of K-theory of Leavitt path algebras. Now, why the K-theory of Leavitt path algebras? Because personally, I was quite interested in algebraic topology at some point, and I used to always appreciate the topological side of it, and always thought that algebra in itself isn't some sort of an consequence of topology, or you just forget some part and then you essentially obtain this. And then during 2 years ago, when I was doing my PhD, then my supervisor posed this problem that whoever is doing Leavitt path algebra, they are experts in K-theorists. So I thought that, okay, this is the prerequisite for that to do study. Now, the thing is that, what is K-theory? Okay, fine. I'll just give you a very basic idea here, because we know that it is, no one is going to do justice to the idea of K-theory by studying it for 10, 15 minutes. But anyways, it's basically a generalized cohomology theory. So I'll use this, use this notation, but please do not write it entirely as a ring. It is just to show that what I want to show thing here. So the Kn of a ring R, it's like this basically happens to be a group. And what is this group? This group is nothing but the homotopy group of something which is very complicated, something which we cannot necessarily encounter at this point of time. But again, since this happens to be a place where we get exposed to new stuff, where we get to see new stuff, and this is a new stuff which you get to see, which I saw 2 years ago, and I started digging up more on this, and maybe you can dig up more on this. But before you do your digging up, before you do your own way of studying these things, what are the things that you will look at? So you look at this group, which is the pi n of, say, a space, a topological space, basically happens to be the homotopy group. It's also called the nth homotopy group of space. And again, it just goes without saying that please don't use it like this. Use space here. I'm just using it so that we are familiar with what are the things that this group in itself is trying to obtain. And this idea of when you go with P, G, and R, right? This is something which basically Quillen did, and for which he got the Fields Medal in 1980 or something. And it's the Flask construction of a topological space. So what he said is that okay, you give me a ring, you give me a ring. This is just an algorithm. So he started with a ring, then takes the general linear group of that ring, then takes the classifying group of that group, or by the classifying space of that group. And he states that, okay, I will do a very nifty trick here, and I will use another space which happens to be bigger than the spectrum. Okay. So at this point of time, we will be treating a lot of these as black boxes, because we have to treat them as black boxes so that we can get the basic idea, so that we can get the ball going forward, and we can just have enough amount of prerequisites set up so that we can move forward. Okay. So the idea of K-theory in itself happens to be something where you start with a ring, you go with the general linear group, then the classifying space, basically called the classifying space. And this is called the Flask construction, or the now. Here comes the idea that the thing is that you can see that here I'm denoting a notion here, and these are n. So how does this n is going to play a role here? So you should be asking that what this n necessarily is. I have said here net homotopy group. Here is this Kn. Okay, so all the homotopic groups or the K groups that we know so far, we do it basically for n which is more than or equals to 0. Now, if anyone here, because they're very much interested in understanding the whole of this K theory, there is one of these seminal paper that I would recommend. And if you essentially can decode most of the results in there, it's very good because that will give you access to K theory from an homotopical perspective. But this is just a motivation of what I necessarily am interested in. Since we can see that the moment you go up into the higher groups, or things becomes a bit complicated. So let us try to understand it from the most simplest one, K0. Because this is where you are starting, right? This is where the game starts. The game starts with n more than equals to 0, and you want to start with the most first step of this game, and the game is K0. So we want the K0 of an united ring R. Now, if you would have paid attention, like if you remember a portion of Arlene's last part of the talk, but she said that given a ring R, okay, you collect all the monoids of finitely generated projective modules over that ring R. And then what you do is that you take its group completion of that. And this group completion of this is nothing but your K0 of the ring. This is the most classical way of doing this stuff. Take a ring R, take all the monoids of monoid of isoclasses of all finitely generated projective modules over this ring R. Then take the group completion of that monoid, and that is essentially nothing but the K0 of that ring. Okay, now why did we go up with this a lot of stuff here? We go here so that we want to study this. But since it's a direct path algebras, we want to study the K0 of LKEs. And it goes without saying that you can study all the other LKEs as well for leave-it path algebra precisely from this paper. But again, the machinery around it is a bit more involved and then what we will get to see here. So if we were to use this, so this was the basic idea of the K theory of leave-it path. We are just concentrating on the basic case, and we want to do this. Fine. We want to compute this one, K0 of LKE. So that means that my ring is nothing but this LKE. I need to know about V of LKE, that is a monoid of finite isoclasses of the monoid of finitely generated projective modules over LKE. And if I can do that, then I can essentially take its group completion, and I should be able to obtain the K0 of LKE as well. But here comes the part. How to obtain this? So, how to obtain V of LKE? And this is where the idea of a graph monoid essentially plays its role. So now we'll go with the theorem. Often at times when we have certain theorems to study stuff, it becomes a bit easier for us to recall and also to collect the data in a much more precise way. So let us take that, let E be a row finite graph. Then for leave-it path algebra K, we have this monoid of LKE to be nothing but ME. Now again, I have thrown in another term in here, which is basically this ME, another symbol appeared into the picture. You wanted to dissect out a symbol, but you are giving out more symbols now. So I'm not necessarily solving the problem here. So how can we solve this? Yeah, sorry. Oh, okay. So sorry. Okay. Okay. I'll go a bit slow. Okay. So we are looking at something which is ME, which is basically the graph monoid. Now you will need a definition to work with it. And before I go into this thing, a few weeks back I was discussing with someone who happens to be something who does K-Pinstick studies purely from an K theory, from a categorical setting. They study purely K infinity categories, all the most difficult terms. So they asked me that, okay, give me this motivation that why should I study leave-it path algebras from an infinity categorical setting? So what is it that this K0 in itself is computing? What is the data that I can get? because at the end of the day, this needs to compute something, right? And now we will see that what it is essentially is taking into account. Okay, so started with a ring, then we have to do this, and I have also thrown in another symbol here, which happens to be this ME. Okay, let's see. So I will give you a definition of this. So this is given a graph E. Should say that. So let 0, E1, then your ME is nothing but the monoid, the free monoid, which you generate over all the vertices, quotiented by a relation. If you take AV, belongs to S inverse of E. I think this I should not be covering here. Okay. So what you have done is that the definition essentially states, I guess we have seen a portion of a monoid structure. The monoid in itself, I believe it's the most natural algebraic structure that there ever exists. It's a set. You take two elements from the set, you combine them out, the resulting element is also in the set. So most natural definition of studying something. Now, this happens to be the monoid, which is associated to this graph. And I'm claiming that now things are starting to get a bit more discrete. Here you have started with the monoid of iso classes of finitely generated projective modules over LKE, and you're connecting it to something which is very discrete in the sense that something which is very much computable. So we are moving from algebra, which happens to be so chaotic, you cannot understand, you cannot move any forward, to something which is somewhat tangible, somewhat can be worked out. Okay, now let's employ this using that theorem. Let's try to do an example. And I have picked up this example. If you want to this. So we go with 1, 2, and 3. So this is it's a graph. It's a graph, right? It's a directed graph. And I guess I came to know about this, that people often get confused between quivers and graphs, essentially the same thing. The only reason being, it was Peter Gabriel who thought that if I were to ever study algebras or something arising out of a graph structure, and if there is a direction associated to it, I will be calling it a quiver, because in English, quiver means an arrow. So whenever you hear the term quiver or graphs, it's basically nothing but a directed graph. Anything with an arrow. Okay, so but I like to call this more of a quivers, but anyway. So if you happens to be a quiver or a graph, which basically looks like this, and I want to compute the graph monoid, means I want to compute this. Okay. So that means I want to look at the free monoid, which is generated by them, B1, B2, and B3. And by free monoid, I essentially mean that not the linear combination, but the natural combination, any word types of words in this B1, B2, and B3. And you quotient it out by relations, right? Relations which are coming from the graph, which basically states that taken any vertex V, which happens to be regular. So if you can obtain this. Now, I believe most of you who are in the masters, they have seen Levitt path algebras. Like anyone who is studying? Anyone who is studied Levitt path algebras in a master's paper? I guess you have seen, right? The definition of Levitt path? Okay. Then because I came to know that this happens to be a paper which is taught in the master's level here, so which is great thing. I really appreciate it. But anyways, so we know what these regular vertices are. These are those which are neither sinks nor infinite emitters. Since you have taken a row finite graph, so the only thing that you need to take care of is sinks, because infinite emission cannot happen, right? Because row finite in the sense that you're in an adjacency matrix, only finitely many terms are non-zero, and all of the other terms are zero. Okay, so that means that I'm looking at all the non-sinks here. Now that I don't have any non-sinks here, so it's fine. I can essentially use all of them. So let us see that what are the relations. So for V1, so it's V2 plus V3. V2 is V1 plus V3. V3, it's V1, it's V2. So I quotiented it out by this relations. We all agree, whoever has seen these things before, yeah, it's fine. Okay. So if we were to quotient it out by that particular relation, then I'll make a bold claim here, and it's up to you to verify that whether my claim essentially holds. Because since it's a monoid, we will need an identity, right? Because it's a monoid. So let us assume that this happens to be the zero element or the identity element in that monoid, along with these many elements in this. And this is my claim. My claim is that my monoid, which I started with, taken all the combinations of V1, V2, V3, quotient it out by this, you should essentially get this. It's a claim, okay? I find in case. So it's my claim, and I'm not going to prove this because it's just an tedious amount of computations which you need to just verify. Now, okay, do a thing here. If you remember the recipe to study K0, the very basic K0, we started with a lot of stuff, but we want to study only the basic one. The recipe for K0 essentially wants that you need to complete, you have to complete this into a group. Unless and until you complete it into a group, you cannot essentially say that this happens to be the K0 of LKG. You need this to be completed. Now, here is a position. The proof is also that if you have let M be a monoid, and let's say G, H, and G, and H is a group, then the group completion, that means H. It's a proper, which basically states that if you start with a monoid, M, and if you say that you are quotiented by 0, then its group completion is nothing but H. So, okay, let's see. MZ quotiented by zeta is basically V1, V2, V3, V1 plus V2 plus V3. Is this a group? Can we try to see that whether it is a group? Like what should be the identity element here? Additively, because we are using this that's zero element, because this happens to be the group, so we need the identity in this. So what do you think should be the identity? Okay, so and we have these relations here as well, right? We do have this relation, because subjected to this relation we obtain this MG. Now since I have 10 minutes, so I cannot if you want to work out, if anyone wants to work out, and just give me, like, let's work it out for 2 minutes. It's not very difficult.
10 minutes.
Oh, 10 minutes. Yes. Okay, then. Okay. So the identity is your V1 plus V2 plus V3. And what is the order of V1? So V1 is, what is V1 plus V1? So it is V1 plus, say if I can write V2 plus V3. V2 plus 3. So I want to write it. So if I go with V1, this is V1 plus V2 plus V3. If I go with V2 plus V2, then instead of V2, I can also write this V1 plus V2 plus V3, and V3 plus V3. So if zero element V1 plus V2 plus V3, and if you add them up every single time, you end up getting the zero element. So what is the order of each of this element? Order of each of this element is 2, right? Because twice V1 is 0, twice V2 is 0, twice V3 is 0. Do we know a group of order 4 where each element is of order 2? A group, there are 4 elements, and each element is of order 2. Apart from the identity, every single element is of order 2. So what is that group? Z2 cross Z2. Oh no, field of 4 elements you will not be able to have. It's Z2 cross Z2 or Z4, the group which is Z4. If you oh no, it will be a non-billion. So K4. Do we agree with this group? Right. Or you can also write it as direct sum. I guess anyone write meaning. But finite products and finite sums are similar, so you can also always twist this to symbols. Okay. So I have essentially computed, what have I computed? We have computed, this happens to be the group completion, okay, by that logic. So fine, using this proposition and using this graph, I have a very nifty way of saying that. Voila. Something which was so technical in the terms that we wanted to do only ring theory, the monoids of finitely generated projective modules, and you have essentially computed this and said that, okay, the K0 of this FKG is nothing but Z2 cross Z2 using some purely discrete settings. So now I have seen that whenever people who are doing math and they try to come up with any result which works in one particular setting, the very next best thing that they try to do is to generalize. So now we have had one thing, so we will let us try and let us generalize. So we have seen that what is this V of LKE? If you remember, this is nothing but ME. And this is, you take the linear combinations, you take not linear combinations, but the natural number combinations of all the vertices quotiented by these relations. So basically, this looks a bit like this by those relations. And what is those? Yeah. Right? Because if you remember, we are not taking linear combinations. We do not write 3v1 plus v. We do not write this. The negativity is not there, right? We just take combinations, the natural number combinations. Okay. So the group completion is I'll just write it a B. And I'll give you what exactly it looks like. And you have Z of greater. Now, what is this ZB? This ZB is an element here in Z where the component corresponding to V is 1 and else it is 0. So let's take in some time. Let's take 2 minutes to just to appreciate what is going on. So we started with something where we say that we take only combinations of integral combinations of the vertices quotiented out by this particular relations. And those relations where, if you remember, it looked a bit like that. If you take the vertex minus all those vertices corresponding to the range of those edges which are coming out of it. And that is exactly what we did. So if we were to use it and mimic it entirely in an algebraic setting, so what we do is that we take that direct sum and see. So it's basically, this one looks like a tuple where there are V not many entries, or sorry, V not many entries. So you are taking all those E naught tuples and you are quotienting out all those E naught tuples by this particular subgroup. So now what happens is, okay, so if this things were to be true, and these are indeed very much true, let's go with this final theorem. And this final theorem will seal the deal into understanding K0 of LKE. But again, this is just the K0. So just from here, like this is just a heuristical way of doing stuff. By heuristics means like we don't have a proof right away. It's from the observation. This is what it should be for the group completion for the B of K. So I have this. So that let E be a row finite graph. And say you take a map phi, it goes from the monoid of classes of rotary modules T, such that you take any element here, vertex T, and you are sending it to that tuple where there is one in the V component and every other point is 0. Then the group completion of LKE if I take this map and I have this. So then the map short is, so what is my K naught then? Quotiented by T. Okay. No, this is for the Z copies. I just so that I can get this isomorphism. Because since this happens to be a group, then I can use that this is the universal group. I can take a map from here. Yes, but the monoid is going to embed inside the group.
Oh, so it's just
Yeah.
it's not a-
No, it's not isomorphism. So the moment you have this, and the moment you have something which looks a lot like an n tuple, which is basically of that many entries as a number of vertices. So you have a very nifty map. So you say that the co-kernel of LKE is nothing but, sorry, the K0 of LKE is nothing but the co-kernel and I know that this map in itself is quite difficult to just to gauge at this point of time, and we don't have that much amount of time. But the reason why I want you to appreciate this map, it's because you may think that this appears only in K0, but that is not the case. If you were to take a Levitt path algebra over any ring R, then do we know the decomposition? It looks a bit like this. Right? This is the decomposition of a Levitt path algebra over a ring. So you just have you studied tensor products? Means like here for I. Of our Z, sorry. So the reason why this thing is advantageous, it's because so that I can just build up to the final remark, which happens to be there. That the higher K theory, it's so funny that there's higher K theory. And the map which you use here, so if I were to say that this map is basically, say I were to call this co-kernel map to be phi, then I get to see this sort of map here. This one.
Sorry, I don't say F or E.
Oh, no, sorry. So what is it that we are trying to build here? We're trying to show that the higher K theory in itself is motivated from the maps which we get to see from this K0. So the very next subsequent thing that people can try is to study K0 of LKE, K1 of LKE. People have been trying to do different flavors of LKEs or different Levit algebraic structures. But my main idea to show you is that even though this exists, which in itself is such a topological way of doing stuff, It is the K0 which can be worked out in a discrete setting. And that is the why graph monoids needs to be appreciated, and which I did not do in the first place, and now I regret it very badly. But anyways, thank you so much for your time. So I think okay, any questions?
It's still on a zero and a one.
Yeah. Oh, K0 is quite easier because it has been worked out quite well. K1 also has got a map, like it's. Oh, that is the thing. That is extremely difficult because the problem starts here. See, the moment you say Kn, this is what happens for n more than or equal to 3. Because still K0, K1, and K2, you have this, these are called classical K theory. The moment you enter K3, you have to enter the third homotopic group of this classifying space. And this has been carried out in different ways. You can study higher K theory from a categorical perspective. You can construct an Waldhausen categories, people do it in that way, or symmetric monoidal categories definition. All of them essentially coincide. My point is that if you ever study this Ara's paper on the K theory of Leavitt path algebras, we will be able to appreciate that why the K theory of Leavitt path algebras are interesting. It's because the K theory of Leavitt path algebra, the C star, the K theory of the topological K theory of C star algebra, as well as the homotopic K theory, they all coincide. So the main goal of this particular talk is to say that something exists out there which is difficult for us to comprehend right now, but out of all those which is difficult to comprehend, something exists which can be computed in a discrete setting. Okay. Yeah. Oh, yeah. Yeah, it's valid for n because I think William did a very nifty trick. What he said is that even though he was not able to compute it for K0 and K1, he said that in those cases, I will not construct the classifying space. I'll just essentially compute the same algebraic K theory that I have been doing. And as a result of which, if we read up any algebraic K theory book, this is the definition that we get to see. So they have incorporated every single thing here, because for a homotopic group of an classifying space, you essentially get back the what is it called? The GLR back, right? And since this is nothing but the BGLR class, that means an topological space which is slightly bigger than BGLR, but not BGLR. So you will be able to accommodate all the K theories here. Okay, thank you.